Starting. Okay. Yes. Thank you. Welcome to the Satellite Working Group meeting. It's a pleasure to have here Professor Jaafar providing a technical presentation entitled Aerial and RIS-assisted Edge Computing for Vehicular Task Offloading. So please, you can provide this interesting presentation.
Thank you, Giovanni. So hello, everyone. Since we are behind schedule, maybe a little bit, I will just try to go fast. I'm professor in software IT engineering department of ETS Montreal. So I will just skip maybe the presentation about ETS. I've been and also I started as professor since 2020. Okay. This is also maybe a glance about my research areas and research team. But for the sake of timing, I will just get directly probably to the technical presentation. So I will talk at first about aerial assisted computation offloading. So the motivation behind computation offloading for vehicular networks comes mainly from the fact that we are developing intelligent transportation services, including navigation, vehicle control, traffic management application. Of course, for now, all this is being done locally on the vehicle. But the problem is that if we anticipate equipment failure, for example, or limited computation power on the vehicle, or limited access to roadside units, so these side units servers that can be available mainly in dense urban areas, well, actually, you might have problems with these services. So the idea is how can we make sure that we have high quality vehicular services with minimal delay that are energy efficient. And what we propose here is to leverage aerial-based edge computing. So aerial-based edge computing, meaning that we will rely on aerial nodes like drones and high altitude platform stations or even satellites to support task offloading or to support edge computing for vehicular networks. In terms of system, this is what we envision. So you have these vehicles, connected and autonomous vehicles that are usually on the road or on highways, and that have intelligent transportation services that need to be satisfied. Of course, in the extreme case where you have some computing server failure in these equipment, you would rely on the aerial platform. So here we might have multiple drones that have computing power, so they have some computing power, and these drones usually they are hovering or flying at altitudes between 50 and 150 meters. The thing is, these communication links are short. And they are limited because actually this type of drones would have limited energy. And then you have the HAPS. So the HAPS is higher. It can go up to 20 kilometers in the sky. It is quasi stationary. And in terms of connectivity, it would cover all the region. And even in terms of computing payload, it would have a lot more capacity. So actually we can deploy more computation capacity in the HAPS compared to the drones. In our investigation of this type of system, we start really easy. So at first, we considered a very simple system where we have one UAV that is deployed to support task offloading from vehicles on a simple road or highway. So the use case is that this drone can be deployed during peak hours. And we considered one drone that is actually flying in a come and go trajectory. So actually, we are not optimizing, or we are not looking to optimize the trajectory of the drone. We are just sending it in the sky and defining edge or extreme points on the highway, and it just comes and goes between these two segment limits or two segment endpoints. In a given way, in stable speed. So it's not accelerating or decelerating. It's just a stable speed in this case. So what we did here is that we considered the communication that would happen between the drone and the vehicles. Of course, we considered a dominated line of sight link because you don't have obstacles or shadowing between of them.
And of course, we have a computing model where actually you have these computing tasks arriving to the drones that enters into queue and then will be processed one by one. So we consider the system simple, where actually we have first in, first out in terms of tasks. And based on that, we have to analyze the energy consumption and the delay, because these are the most important things we have to do here. So for the drone, we have some task processing energy that have to be calculated based on the processing power that is defined on the drone. And also it needs important energy for traveling, for flying from one side of the highway to another side. And then we have the total consumed power energy that have been defined. In terms of delay, actually, we relay that first. What you see here is the achievable data rate using the Shannon formula. But since the vehicle is moving and the drone is moving at the same time, the distance between them, it is changing. And because of that, the data rate would change over time. So we defined a different way of data rate in order to show that the necessary time that is needed to offload alpha M data from the vehicle to the drone will need to go through a certain number of time slots. So here, of course, we assume that time is discretized into time slots. And then you might have a delay for data queuing, because you might have many tasks arriving to the drone. And also you have the delay for data processing. And of course, total delay is the summation of all of it. Then what we did is that we formulated the problem of maximizing the task offloading success ratio at the drone. So without looking, too much into the equations, we want to make the drone satisfying as much tasks coming from the vehicles as possible. Of course, by respecting task offloading delay threshold, which is QM. And of course, by respecting that the whole energy that have been consumed respects some battery capacity value. Of course, I mentioned that we are not optimizing the trajectory, but the only thing that we are optimizing here is the launching point and the launching direction. So actually here it's the launching point location of the drone and the initial flying direction that it will go. And of course, we need to decide on which tasks will be associated to the drone. So to solve it, we really used simple genetic algorithm task offloading method at first. So I'm not going to through the details, but that's the typical solution we have used. Why? The motivation behind is that genetic algorithm, even though it's slow in converging, theoretically, if you let it run enough time, it will get you to some optimal or near optimal solution. And we compared with another, what we call iterative exhaustive linear programming based task offloading approach. So in this one, we have made exhaustive search about some parameters, which are the launching point and the directions. So we have considered that our segment can be divided into a discrete number of launching points, and we also have right on left direction. So this was the exhaustive search, and once you fix the initial location and the direction, actually the only problem that is left is assigning or deciding to assigning tasks to the drone. And this problem is a linear programming problem. So actually you may use any optimization tool like CVX to solve it. So in our simulation, we considered a number of benchmarks where actually we randomly select from where the drone is launched, or actually always presetting the same location to be launched. And we took also best launch or average best launch location for the drone. So here we have some parameters. I won't go through all of it due to time limitations. But what is interesting to see here is that we looked into the task offloading success ratio given different data size, so the task data size. And what is interesting to see is the green and the purple ones, which are genetic algorithm and EULP solutions. So you see here they're providing the best success ratio compared to the other benchmarks. And of course, the bigger the task, it takes more time to send it, to process it, so it will affect the delay constraint, and that's why the success ratio is decreasing. However, you see that the genetic algorithm and the ELP, they get you something still robust compared to the benchmarks. Of course, I want to highlight here the execution time of these algorithms. So you can see that the benchmarks are very fast, are below the 1 second. The ELP is somewhere like between 1 and 1.5, or actually here up to 3.7 seconds. But genetic algorithm is really very slow, so more than 77 or 80 seconds here, and it goes even up. So of course, in terms of best solution, we have ELP is really the best one in this case. We did some more simulations here. For example, different road length have been considered. So the highway is either 1 kilometer, 2, 3, 4, 5, with the extremes have been used by the UAV to come and go. And again, we see that the genetic algorithm ELP, they are doing great. They are around the 90% success ratio compared to the other ones. So that was the first use case with one drone. So here in second use case, we complexify the system. So first we considered multiple drones, and we considered that we can cooperate with the HAPS. So HAPS and these multiple drones can support tasks coming from the vehicles. In addition, so because of that, actually there are multiple communication links. So we have the classical communication links with the drone, but we have other communication links between drone and HAPS, and even for feedback between HAPS and the vehicle. So we have more complex links here. We have considered now not just line of sight. So here we have probabilistic channel model where you might consider line of sight and non-line of sight link between the drone and the vehicles. And also we have line of sight only for whatever thing that are aerial between UAVs or UAV and HAPS. And here to add more complexity, we considered that a task can be subdivided to subtasks. So meaning that to execute a task, you have to execute numerous subtasks that have some logical or virtual links between them. So the link can be linear. For example, I have 4 subtasks that have to wait for each other to be executed. It can be in parallel, like this way, or that can be hybrid. So this complexifies even the problem more, because now we are not just uploading tasks, but we are uploading subtasks and ensuring that there is the link between them. And all of this, of course, will affect the delay of the service. So without going through all of this, here just to show you that because of this dependency between the subtasks, you have to account for the time that you are waiting to get the outcome from a previous subtask to execute the current subtask, etc. So this is just to show you a little bit that is more complex here to calculate the delay. And also, of course, to calculate the energy consumption, again, we have to account for processing per subtask, plus the energy that we have used here, for example, for feedback. This is something that we added compared to the previous case. And of course, since vehicles are covered by the UAVs, so whenever we want to, whenever we have this movement of the UAV away from the initial drone that was covering it and it goes to another one, actually you have to account for that in order to get the feedback to the right drone that is covering now, after some time, the vehicle. For the HAPS, we have also another equation for, of course, for energy consumption, so which is similar. Here, the problem is slightly more complex. So we want to maximize 2 things: task offloading, as previously, but also the residual energy of the system, meaning that we want to maximize energy efficiency of the system that is represented by the drones and the HAPS. Of course, constraints are still the same with the delay threshold, with the UAV and HAPS battery capacity, and of course, a subtask cannot assign to more than one node. And here, the problem here is about task assignment only. So we want to make sure that the subtasks actually are assigned in the best way possible to respect all these constraints and maximize our objective. So here the solution was based on genetic algorithm. It is more complex, of course, than the previous case, but we adapted to our new system. And without going through all the simulations here, we consider the case with one HAPS. And if I'm not mistaken, we have 3 UAVs. Yeah, I'm just trying to make sure. Yeah, it was not mentioned, but we have 3 UAVs. And then we have some parameters regarding the threshold on the delay. Also, we have divided the subtask into hybrid subtasks here in our simulations. Here, benchmarks are different. So we have fully local, where all tasks are offloaded to the UAVs that are covering the vehicles. Random offloading, meaning you put it the way you want. And then capacity-based offloading, where actually we'll prioritize putting subtasks in nodes that have larger, that has higher computation capacity. And full HAPS, meaning we put everything on the HAPS only, so we don't use the UAVs. So here we look to the success rate in 3 traffic conditions, where actually have low traffic vehicles, medium traffic, high traffic. And as you can see, genetic algorithm is reaching about 80% here. It's close here. It gets down to 60%. And you see that capacity-based offloading, which is a heuristic, and the full HAPS are following closely, especially in the case of high traffic. So high traffic here, they are very close, but still genetic algorithm is providing the best result. And if you look into the average energy consumption, here it's interesting because you see that genetic algorithm is not so bad. It's not really consuming a lot of energy compared, for example, to full HAPS or the other ones. But of course, this is compensated by the fact that we are satisfying more services or more tasks here. And here, these are also like other results where actually we considered different subtask division models. So you remember I talked about the linear, parallel, and hybrid model. And here we looked into these differences. And in all cases, you see that genetic algorithm, the blue one, is having the highest service rate. And of course, the energy consumption here is low. Just to clarify, these results are only for the low traffic, okay? So of course, if you consider other cases, the energy consumption will be higher. So that was for this cooperation between UAVs and HAPS. And what we did in this final third contribution, we tried to push further the energy consumption by leveraging reconfigurable intelligent surface. Why? Because we can use passive RIS for signal forwarding or data forwarding without really consuming or using an active antenna in that case. So the idea, so if you're not familiar, of course, with RIS, RIS allows you to steer or to redirect RF signal in a controlled way in the direction you would like, of course. So you can do beam focusing, absorption, imaging, scattering, and polarization. And the idea was to equip these aerial platforms with the RIS. So actually, this idea we launched this idea a few years ago in our group, and we proposed actually to equip RIS on the drones, on the HAPS, on satellites. And also, we did some link budget analysis about it to see if it's feasible. And the short answer is yes, it is possible to use it. And this is what we leverage here in our new system. So here, we consider that our drones, they also have RIS. So actually, they have active antennas, they have RIS, and they have edge computing. And the HAPS here, to make it simple, we didn't consider that it has RIS. So it only have antennas and edge computing. So now you have this more complex operation because you have different modes that can be used at the drones, either as an edge server, RIS-based relaying, or active antenna relaying, or transmitting or receiving. So the same assumptions are kept here compared to the previous one. The same task, also division into subtasks, have been considered. But here, because we have the RIS, the communication model is slightly different. So we have direct communications when we use the antennas, active antennas, but we also have this relaying through the RIS. So we consider that the RIS can relay the signal coming from vehicles to other UAVs or to the HAPS for processing the tasks. So without going all through these details, I would just maybe talk about this example. So here we consider that we have subtasks 1, 2, 3, and 4, and the assignment has been done into different nodes between UAV1 and UAV2 and the HAPS. So here, of course, because of this architecture of the subtasks, you need to execute 1 and 2, then you need to send the result to number 3, and then send the result to number 4, and send it back to the vehicle. And we had to account for all this communication, all this processing for the end-to-end delay. So this is what we did. And of course, including the queuing time. The objective is very similar to the previous one. So actually, it's almost the same thing. With the difference is that when we calculate the delay, we have to account with what happens with the RIS. So if we are using the RIS, then we have to account for it. And here, optimization parameter is not just about assigning tasks. So that was the previous parameter that we had to optimize, but also we are optimizing the transmit power at the HAPS and the UAVs, of course, because they need to send the outcome of a subtask processing to another node. And of course, we need to look into phase shift configuration at the RIS that is used on these HAPS. So because of this complexity and that we have many parameters to optimize, we adopted an alternative optimization approach where we fix some parameters and we optimize the last one. And we did this in an iterative manner, so between task assignment, phase shift configuration, and power control to get the results. So we had to solve these sub-problems separately at first. The first one is about task assignment, so assuming that power and phase shift have been given or have been fixed. So we have to look into this problem. The problem is nonlinear, so we have to linearize the constraint, introduce some slack or auxiliary variable, and apply McCormick relaxation. So we changed it to mixed integer linear programming, MILP formulation, and then we solve it with the Gurubi on some optimization tool. For the second one about phase shift configuration, we applied actually successive convex approximation after transformation into positive semi-definite matrix for the phase shift expressions, and then we applied EVD to extract phase shift configuration. So once we get this, we just solve it using CVX. And the third problem for power control, actually, we derived a closed form expression for power control, for power allocation, based on the constraint that we have to respect. So mainly, we need to have enough power to respect our deadline, like the delay constraint, and of course, with respect to the maximum power that is available there. So we derived the expression. I'm not showing them here, but we derived them and use them for power control. So these are some parameters. I'm not going to through it again, but we have 1 HAPS, 3 UAVs also in this case. And we consider it different energy budget for them and a different also CPU power. The benchmarks are slightly similar to previously. So this one, random phase shift, is exactly the same as what we propose here with alternative optimization, but we didn't optimize the phase shift. We only optimized power and task assignment only. Full HAPS is as previously. Equilibrium offloading. This one is a heuristic that makes sure that we have balancing of tasks offloading to different nodes in the network. Local offloading is offloading only to the UAVs without the HAPS. And previous work is actually what I showed you before with the genetic algorithm, but without using the RIS. And in terms of results, so actually the blue lines, what you see here is what we have proposed. And we see the success rate actually is the highest in different traffic condition. And of course, we have looked to the energy consumption. So we can see here, in this case, actually, our energy consumption, when the traffic is more intense, we consume more. So even the highest compared even to the full HAPS case. But to have a fair comparison, actually, we divided the energy by the number of satisfied tasks. So it's the energy per satisfied task here. And if you look now, you see that our methods actually is not consuming that much compared to the other ones. The HAPS has the highest, so actually it consumes a lot of energy to process all the tasks that is successfully delivering. But you can see ours actually, you can see it's low. It's even like in the case of high traffic, actually is even low as fully local. So actually it gives us an indication that of course here we are putting more tasks in the UAVs, but we are also using the HAPS. Why? Because our performance here is a way better than the other ones, as you can see here. We also looked into performance with the length of the highway. So this is similar to what previously, but with the RIS. So actually, the success rate is also very good with our method compared to the other ones. And that's it. So just to conclude about this presentation, so we have robust approaches for dependency-aware task offloading in cooperative aerial assisted vehicular networks. We have taken advantage at first by using the aerial platforms and then by adding the RIS within the UAVs. So this multi-mode operation of the drones here with RIS, with antennas, with edge computing actually would become mainstream in the future. But of course, these results are very well for offline, so it gives you a reference performance. But the idea is really to deploy it online. So if you deploy it in real time or online, you would look maybe to different approaches that would involve maybe multi-agent, would involve reinforcement learning or other approaches in this case. So thank you, everyone. If you have any questions.
Thank you very much, Wael, for your interesting presentation. I think we have time for a question from the participant. And in the meantime, maybe I could ask you if you can elaborate a little bit more on the use cases or the application for this, because maybe this is something good, interesting for all.
Yes, so actually the use case, I mean, the first use case when I mentioned it about using UAV in a temporary way is mainly because we want to support the vehicles, for example, where actually you don't have, for example, roadside units to provide you with navigation information, for example. Like something is happening, there is some accidents on the road ahead, and this information you are not getting it. So this is about the connectivity part. But of course, there's the part which is related to the tasks or the edge computing. And here it depends on what's happening on your vehicle, because if you use your servers and vehicle power to do critical and non-critical services, and if you even consider that you even dedicate some of its power to help other vehicles, because you can use also V2V communication, vehicle-to-vehicle communication, at some point you might lack maybe some enough power, for example, to process images from the cameras around the car, to detect objects, to detect obstacles, etc. Or even you have failure in your own server. And in this case, the communication part would be always working. So actually, for example, your cameras are still working. You are collecting, you are looking into videos or images, but you don't have enough power to process it. And that's why we leverage these non-terrestrial nodes to do that. Of course, drones, it's nice, but drones cannot be staying in the sky for long unless actually you maybe use some fixed wing UAVs. So that's why we leverage also the HAPS, because the HAPS has the advantage of covering a bigger area, and also it has a higher payload. So in this case, we can offload to it. And if I want to push it to the extreme case, is that I want to do, for example, remote driving, not just autonomous, so remote driving from somewhere else. So actually, we can leverage this through the HAPS or the drones to do that.
Yeah. So, yeah, I think, there are interesting scenarios that are thinking future applications. I have okay, no, that's a spam phone, spam call. Okay, so is there any other strange? Is there any other question from the participant? I think we have people. Yeah. Pat.
Yeah, I think while I was just thinking about the V2V case and the automotive case, which will become very, very important in the next couple of years as more autonomous cars and semi-automatic autonomous cars enter the roads, so that for situations like early warning, advanced warning of a obstacle up ahead or some trouble ahead on the motorway at particular times of the day, certain highways would definitely benefit from RIS. Maybe they wouldn't actually use drones. They could use beacons at various points along the highway. Is that something that can be considered? And the other question would be, how do you think the operators, the MNOs, will they want to monetize RIS payloads, or will they have a lower cost for that? Because if it's a lower cost, it becomes more attractive for HAPS or drones to use RIS instead of using regular cellular, and it actually may relieve congestion on the cellular for high priority messages like that. That sort of idea.
Okay, thank you, Pat. So regarding the first question, is that actually, of course, here we put the RIS on the drones, but because we are taking extreme case where actually you are in the middle of nowhere, probably. But if you are in urban areas or suburban areas, you might put those RIS, like, you know, on the windows of or facades of some buildings, and it would work, of course, very well that way. So here, I mean, I pushed it really to the extreme case by putting it on the drones. And regarding the second part, of course, RIS is interesting for operators because they know actually with the RIS they can control signals. So actually they can reduce interference in their communications. They can extend communication range with the RIS. So of course they will be considering this because their deployment cost will be dropping, of course. So now about the cost of the RIS itself, I don't know how much it will cost, because until now I know that there are many groups that are trying to actually they start building and fabricating RIS, and they are, even some of them are already working. But from what I know is that currently the RIS is not that expensive. And I would say this is mainly from what I know is regarding the indoor RIS. So indoor RIS will be easier, of course, to do. Here we are looking to outdoor RIS. So outdoor RIS probably it will be more expensive, but if for an operator the gain is there, because rather than, you know, deploying some new small cell, he will just put a RIS and it costs half price. He will do that.
Very good. And the other question I have was probably another application for this is the dreaded advertisers, you know, the idea of the blip in the sky, the HAP floating overhead the traffic would be an opportunity to just reflect advertising, or even advertising hoarding with RIS on them could be used to send messages to the cars quietly, I think, you know, silently, and advertising kind of stuff. But location-based advertising, you know, the usual location-based advertising.
You mean advertising? You mean advertising like using the HAPS as a point to send advertising data or information?
True.
Or
true, yeah, true in the locality. So if you're driving through an area, RIS could be used as an alternative to cellular to just send passive advertising about cheap fuel prices, or, you know, the usual stuff, you know.
Okay.
When you're in proximity.
Okay, I think this is more the HAPS work, because the RIS, I mean, at least here the RIS is passive, so actually the RIS is just some sort of reflector, but you might use RIS in conjunction with antennas, of course, and in this case it will just help you to improve better your signal. So actually you can focus it on like, for example, if you want to focus on a highway, you can do that. Of course.
Or it could be in tunnels, or maybe in tunnels as well. In tunnels, yeah. Those kind of places.
Exactly.
Lovely.
Yeah,
that's all my question.
Thank you.
Thank you very much.
Thank you very much. I don't know if there are other questions. in any case, we are quite close to the end. If there is no other question, I'd like to thank you so much, Professor Jaafar, for providing this interesting presentation. And it's a good opportunity for all of us. So